Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
So we played around a little bit in our previous video tutorial on the basic script for identifying, estimating our urban heat map or urban heat island or urban hotspot, whatever you want to call it. So we played around and we came to the conclusion that, again, bare soils and summer is a problem for my region of interest, for my area. If you want to do classification, identification, classification, etc., summer is out. Don't go for summer simply because of the sheer volume of bare soil sand that's present in this west coast area. Because it's winter rainfall and it's basically most of the land is under agriculture, wheat production and stuff, stay away. And then we also said that in this particular case, the mean reducer seems to be performing a little bit better than the median reducer. Okay, so, and then we worked on anomalies, etc., etc. So that was done in 164. Okay, so that was done in 164. So that's a continuation of 163 and 162. Okay. Yeah, I'm not going to say much more about the numbers here. As I said in a previous video, as they say, go ahead, make my day, press those buttons. Okay, so please press those buttons. Let's get those numbers up. It makes a world of difference. And let's grow the channel together. So this particular video tutorial is a little bit more tricky. So let me put it up there, is that this is quite a, for me, a tricky script. There's lots of ins and outs, lots of problems that I had, lots of help, etc., etc. So I got the script now. I'm not fully confident with the script, so let me put it up straight there. There's one or two things that I don't fully understand. I'm still learning the script, trying to figure out exactly what is doing what, but the script works and it does what it says it's going to do. So I'm jumping the gun a little bit because we're on this journey of urban heat maps or urban heat islands or hotspots. I thought, let's do this with the understanding that I still have question marks around the script, but nonetheless, the script works. And I think it has quite a bit of potential. So it's still hot urban heat maps, urban heat islands or hotspots. So it's a continuation. You'll see there, it's our normal stuff. And in this case, where our previous scripts only focused on a heat island for 2023. It's for a period. You'll see that's for that specific period. In this case, I wanted to build hotspots for my 4 periods. Okay, so wanted to have a look and see what happened with this over time. Because a once-off image is what it is. It's a once-off image. It's a particular picture of this in time. And I wanted to say, okay, but how did it change over time? So sort of a temporal difference type of idea. Okay, so when I'm using the loop functions, etc., etc. Anyway, so there's my time periods. Same time as which we started initially, which is these ones here and stuff. So same time periods, again, all winter. Huh? You can see they all are winter periods. Staying away from summer, like the pest, like the plague, staying away. Okay, so I've got that. So up to here, nothing funny, all still same things. Then again, nothing different. I'm using my modus data set. I clip it. And I scale it with that 0.02 as per the data set, and I subtract it by 273 to generate Celsius, from Kelvin to Celsius, and I rename this land surface temperature, LST. Okay, and it's a float. Okay, so nothing strange there as well, nothing weird. So now I've got X number of images, because remember this is image collection, so and I think it's 8 days, 8 day images. So you can make the number. So from 25th, the 5th month, May, to May, June, July, August. It's the 10th month, August, so it's well, 3 months, 4 months. So it's basically 4 months, and so 8 days. So that's four. That's what's it? Five. It's 20, 25 images. If I'm correct, it's 25 images. So for each of these time periods, there's roughly 25 images. I'm guessing now. You can fact check me, but it's not going to be that different. So there's plus minus 25 images. And obviously, what we're going to do is we want to clip it only for our region of interest and stuff. So now we've got the 25 images, okay, which is clipped, converted, etc., etc. So we've got that for each. So we would have now 25 times almost 100 images for these 4 periods and stuff. Okay, so we've got the images there. Yeah, this is just a time series chart. This is to create this. I'm not going to spend too much time on the charts for now. I want to spend time on the images. Okay, so we're going to leave this alone and stuff. Okay, so once we've done now, remember we have now, for each of these periods, we have plus minus 25 images. That gives us plus minus 100 images. So obviously we want to reduce that down to 4 images. 1 image per time period. Okay. 1 image for 2014, 1 image for 2018, 1 image for 2020, 1 image for 20. So we're going to have to reduce the 25 images in each period to get the periods. And we're going to do that by 2 things. We're going to use the mean. Okay, so we're going to do the mean. So we're going to take our, where is it now? Yeah, we're going to take our image, and we're going to reduce it by the mean. Okay, and basically on that band. Okay, so don't worry about this for now. This is just to create this. Sorry, this is just to create the chart. So calculate the mean. Okay, so we're going to calculate the mean. We're going to take the start and the end date for each time period, and we're going to generate the mean. Okay, so now we've created a mean value or mean image for each of these 4 time periods. Okay, based on the select, based on our a band LST, which is this band here, which is now uh, scaled and converted into Celsius. Okay, so we've got that now. Okay, so we've got that value now. Calculate the mean LST. That's now the mean value for the whole region of interest for each month. Okay, so we've got for that period a single value, mean value, land surface temperature, a single land surface temperature value, a single land surface temperature value, and a single land surface temperature value. Because remember, we need that value so that we can identify locations which has either above that or below that. And the idea is if those areas that have a actual temperature of above the mean, then that is typically your urban areas. Okay, so that's the whole idea, remember? So we generate, where are we now? We generate a value for that. Okay, a mean value. And again, you can use, here we go, we can use the median or whatever value that's up to you. Okay, function urban heat islands. So we're going to create now a function which is called urban hotspots. So that's the function that we're creating now. We're taking our mean, a variable that we're going to create as our mean. We take our image and we reduce it to the mean. So now we get a mean image. Okay, we get a mean image. So that is not the mean value for the whole. So that basically means is we take, for those periods, we generate a mean image, which is different to this where we create a mean statistic. So the mean statistic will be one number for that whole period. So the mean land surface temperature for my whole region of interest will be X or Y, whatever the case, for each of those periods. Where in this case, we generate a mean image for this whole region of interest. So for each of these, there will be an image for my region of interest for each period, and the values of each pixels will be a mean value of all those images for those periods. I hope I'm conveying it in a matter that is understandable. I hope so. If not, I do apologize. But yeah, so let me just try it again, maybe a third time lucky. So what we're doing here is we calculate the mean value for our land surface temperatures. Okay, so that means a value for my whole region of interest. So the mean land surface temperature for that period, or for my region of interest as a whole for that period, was X. And then here we calculate it for all of the locations, meaning every pixel. So that pixel has a mean value, that pixel, and that mean value is the mean for all 25 images. I hope that makes sense. Okay, and we also calculate a standard deviation. Also calculate the standard deviation based on our land surface temperature band. Remember our land surface. The best effort is we add it in here. Again, you don't have to do it. It's up to you. But it's trying to find the best number. It uses the best resources to get that number. Again, that is up to you. You don't have to use it, but as I said, it is just a little thing that you can add in, basically to help and assist the program. Okay, so that's something that one can do. Okay, so as I said, it's not something that you have to do, but you can do it, and it does help the system to find the best numbers. Okay, so now we have a mean image and a standard deviation image for each of these periods. Okay, so we'll have a mean image. Okay, first of all, we have a mean value for the whole period from our region of interest. Then we'll have a mean image and a standard deviation image for this period. We'll have a single mean value for the whole period, and then we'll have a mean image and a standard deviation image for this period, etc., etc. Okay, so that's what we've done up to now. Because remember, we want to subtract the two. Then we're going to calculate the threshold. Now, in this case, remember in the previous instances, we basically give him the arbitrary threshold. We're saying this is the threshold. Okay. In this particular case, we are calculating the threshold by using a rule. And what is the rule? The rule is you take the mean and you add the standard deviation multiply 1.5. So whatever the mean is, okay, you take the standard deviation of that mean, you multiply it 1.25 and you add it to the mean. So let's say the standard deviation is 2. Let's say the mean is 5 and the standard deviation is 2. Okay, so then you're going to take the 2, you're going to multiply it by 1.5. So that will give you, 2 times 1.5 is 3. Where's my math now? Yeah, so that's 3. And then you add it back to, where would we start? We said it's 5. So it's 5 and the standard deviation is 2. So we take the 2, we multiply it by 1.5. That gives us 3. We take the 3, we add it to the 5, and that gives a value of 8. So that means that anything above 8, in our case, would then be classified as a urban heat island or hotspot. Okay, so this is what we're doing here. Okay, this is what we're doing here. That's why we calculate the mean and the standard deviation. So for each of those locations, for each of my time periods, we take my whole region of interest, and within that region of interest, we take for each pixel, we calculate its mean and its standard deviation. Okay. Then we're saying, okay, let's then determine whether that's an urban, or that's a heat map or not, is by taking its mean, and then taking its standard deviation, we multiply the standard deviation by 1.5, we add it back to the mean, and if that value is then more than that threshold, then we classify it as an urban heat map or urban hotspot. Okay, so remember the mean is the value, the mean pixel value is the mean value of all 25 images. And therefore there's 25 images, so therefore we'll have a mean value and we'll have a standard deviation. And we'll have a standard deviation. I hope that makes sense. That's what we've done there. Okay. And as I said, we create this automatic threshold. In the previous ones, we gave it a threshold, 0.05 or whatever the case might be. In this case, we calculate the threshold. Now, that 1.5 is purely arbitrary. And you can play around with that 1.5. Okay, you can play around with that 1.5. Make it 2 and see what happens. Make it 0.5 and see what happens. Okay. And my experience so far is that it's very sensitive to this 1.5. So your urban or your threshold, your urban heat map, your urban heat island or hotspot is very sensitive to this 1.5. Okay, so play around with that. As I said, it's very, very sensitive. Okay, and then obviously we're gonna mask it if it's less than that. If it's less than that, it's then mask. Okay, so that's with the greater. Okay, so that's what we're doing here. Okay, so far we've got our image, we've got our time periods, we've created a mean statistic for each of our periods for our region of interest, and then we a mean image, a standard deviation image, and we created the threshold, and we can identify that urban heat islands or hotspots. Okay. So that's what we've done there. And basically, let me go a little bit closer. And that's basically, okay, so let's quickly go for them. There's hotspot 2014. Okay, because remember, this is what we've done now. Okay, this is what we've done now. Is this hotspot? Let me see if we're gonna do this now. Let me just quickly hotspots. There's my hotspots and identify hotspots. Okay, so there it is. So I'm not going to go for this for now. Let's park that now. But basically what we get is, okay, so let's go back. So this is hotspot 2014. So there it sits. So you can again see that it's not very representative. There's lots of areas that's not being covered. So that is very evident. It's underrepresenting. So that's evident. So again, we will have to make adjustments to our threshold rule here to make changes there. Okay, but then unless that's 2014, let's have a look at 2018. Okay, so that's 2018. Let's take 2014 away. And you can see that's 2018 and that's 2014. So a bit of expansion, etc., etc. That is now 2020. 2020. Let's have a look at that. Sorry about that. Okay, it's not going all of a sudden, phones ringing, people here, etc., etc. That's why I don't like to do this at the office. But anyway. Okay, so it just gives you an idea of this sensitivity of this 1.5. So we need to give it a change there. But you can see there's some differences. So that's 2023. Let's go to 2022. So that's 2022. That's 2023. So you can clearly see an expansion there. So 23 starts to look, well, it could be that 24 was just, sorry, there's a hotspot. It just could be that 24 was just this, but I doubt it. There's definitely, I mean, you're missing some important parts, this part of Cape Town and this part. That was there by 2020, 2014. So again, we may need to adapt and to change this. But the point is that we now have 4 hotspot images. And there is definitely some changes occurring. You can see that one there. There's a couple of other places here which weren't there or expand. So it keeps the core, which is good news. It keeps the core of this and it sort of expands out, which is exactly what we would think would be the growth or the change in the city on the urban area itself. So that's, I think, quite neat in that basically we are using this script, the basic script of hotspots, and we're just duplicating for in a time series format, in a temporal difference format, which I think is noteworthy and it's good. And then we automate the threshold. But I said automating, it's a rule based. So we're not automating it per se because this is still a manual part. We could just basically put this a number in there as well and leave that alone. Similar to what we've done with all our others is just to say we're going to give it a threshold, and we're going to add our own number in here. Where is it? Like what we've done there. But in this case, we decided to make it a rule, meaning the mean, and then the standard deviation, and the standard deviation multiplied by 1.5. So I said, if we make this bigger, let's say 2, then obviously our areas. Okay, so let's just do that. Let's make it 2 at 12. So have a mental picture of this. So let's just quickly go into our images and select our hotspots. So that's 2014. You can see that it's much less now. That's 2018. You can see it's almost nothing because the number is so high. So this is extreme numbers. This is extreme because that number will be very, very high now. So if we make it 0.5, then obviously it will be much more because the value is much lower. That threshold value is lower. You'll see there. Okay, so you can see there. So that's 2014. You can see the significance between 1.5. So this looks very similar to this almost. To this. Okay, so let's make it 0.9. Run it now. Should be less areas. Let's just quickly where's hotspots there. Okay, so this looks quite similar to this. So that looks more. So if we do that, and let's say we're going to do then 2014, there's a bit of expansion there. Take 2014 away. So there's some expansion, but not much. That's for 2020. Some expansion again. And 2013, some expansion again, but only this side around it. So what is encouraging is that you have your core and then it expands as time progresses, which suggests that the method is actually quite sound. The method is actually quite sound. Whether it is accurate, that's obviously a different question. Whether it's accurate is a different question, but the method seems to be quite sound and it seems to be logic, etc., etc. But it all depends on this value. You'll see how sensitive. The smaller that value is, the more inverted commas urban areas. The higher that variable, the number is, quote unquote, the less the urban areas. So that's quite important. So that is basically, and then it loops for all these 4 different periods. So although it's one piece of code, it will then loop through these 4 periods and basically repeats itself so that we have 4 images. We don't have to rewrite, copy and paste, copy and paste, and copy and paste. So that's quite neat, this part here. Now, I'm not going to really go through the time series. We've already built that time series. This is similar that we did previously. So I'm not going to worry too much. The main thing is the images. That's what we're looking for, is these images. And that's basically to track the evolution of this urban area or build up areas within this region of interest. So we're not going to go through the chart. That's basically that, etc. So what's important is the method behind creating these images and to visualize these images. Okay, so that's quite important. Then there's something else which we call the UA intensity, calculate the urban heat intensity. That's included in the script. Then there's something interesting where we actually using this particular data set. And this is the data set here. This is the data set here. Which is basically just South Africa. And then we basically, where is it now? I could have used a, sorry, let me just go back there. A shapefile as an asset to do this, but we just take it from the, where is it now? Where is it now? Have I lost it? I'm in the wrong damn thing. So we could have just said urban is equal to a asset here. We just did this. But basically what I've done is I wanted to generate and take my region of interest and divide it into two parts, an urban part and a rural part. So that's what I wanted to do. Okay, so this is what we're doing actually in this part, is to subdivide my region of interest into an urban part and to a rural part. But anyway, that's neither here, neither there, because we're using our hotspot method to generate what is urban and what is not urban. So that's really not too much. But if you're worried, what we're doing here is we're just taking this for South Africa as a whole. Okay, so this is South Africa, we're saying that. And then we just classify it then by urban and rural for my region of interest. So that's my region of interest. Okay, so that's my region of interest. What else is there in this? Oh, we just generate a map for the early period and the latter period, which is basically that, which is a temporal different image. So that's what we're basically doing here, and that's creating this image. So it's just remember the early period, it automatically will take that as the early period, not automatically, because we're saying our early period. Where is it now again? Hey, I keep on losing my place. My early period is 0, okay? And my latter period is 3. And I think we've done it in one of the previous videos, where we say which one is our latter and which one is our early. So if we want our early period, so in this case, period 0 or number 0, which will be this one. Remember, it's 0, 1, 0, 1, 2, 3. Okay, so that's 0. So if we want to make that our early period, 2018, remember, then we'll make that a 1. Or if we want to make this one, which is period 2, 0, 1, 2, then we just change that to 2. And that will automatically capture those dates and generate an image for each, the early period and latter period. And then it will just subtract the 2 periods and then it will display it. So that's a temporal difference land surface temperature image that we now generate. For just go generate the plot to time series. Those are these things. I'm not going to really go much for that, but it's interesting to have a look at these time series plots for what it's worth and to export it for the data itself. Okay, so basically what we're doing in this code is two things really. One is to generate a heat map for each of those time periods so that we can look at the evolution of this heat map over time. And then second of all, we calculate the temporal difference image for our land surface temperature based on, call it a pulled or a script that runs itself. I don't know what's the right word for that now. I don't know where my words are now. But anyway, so this is the script for this. It's a fairly lengthy, complicated script. As I said, I have to be honest, there's one or two places which boggles my mind as well. But with lots of help and support and this and that, I figured it out. But figuring it out in terms of making the work without really understanding why I'm doing that, that is still something I need to figure out. And the thing is, the more you play with this, and that I think is part of this journey, is that the more you play with this, the more you start understanding what the script actually does, what the code actually does, rather than just it must be there so it works. Because that in this script to a large degree is where I am. I have to do that. I have to include it because it works. But I don't fully understand the logic behind it, the reasoning behind it. But anyway, we'll get there. We'll get there. And that is the beauty of this journey. Is that remember we're exploring, and we're going where we have boldly not gone before. Certainly, this is where I haven't been before. And so this is pretty much for me as much of a learning curve that it is for people in my shoes. There's obviously people that understand this much better than I am. But yeah, so this is how we learn. We learn, we take this script, we digest it, we try to understand. So for example, best effort. First time I've used it, it came as a suggestion. And so I've used it. I don't know that it makes a huge difference, but they say it makes a difference. So let's keep it then in, etc., etc. So yeah, let's take it for what it is. It's a script. It's a script to do certain things, which I would like. That is my priority. The details of the script is a bit fuzzy, but we'll get there. We'll get there. We'll get there. But yeah, this is still working on urban heat maps, urban heat islands, urban hotspots, whatever you don't cake, just an evolution of it in terms of using a script that generates multiple images that gives us the evolution of this thing over time. And that is really what I wanted to get to, is how does that change over time, and does that make sense? Does that make sense? And to a large degree, the answer is yes, it does make sense. Okay, so yeah, apologies for not being crystal clear on some of these things. I do apologize, but as I said, it's also new territory to me, and I also have to learn it as we go along. But we'll get better, that's for sure. We'll definitely get better. Anyway, with that said, thank you very much. Thanks for your support. I really, really appreciate it. As I said, we're in this together. Together we're in this. As Yoda would say, be the force with us all, because we need this. So let the force be with you. And with that, I'll see you on the other side.